Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Kurt Shuler of Arteris IP, who's going to explain today what is a network-on-chip interconnect. So, Kurt, when we mention interconnect, it means a lot of things to a lot of people depending upon where they are in the supply chain or the design chain of any chip or system. So, what do you see? What fits where?
It's probably best if I answer this question by doing a little drawing on the board. Okay.
So, Kurt, what are we looking at here?
So what I've done is I've taken the kind of the bill of materials of a complex system and laid it out onto a matrix here. And what we have is this scale here is latency. So for what goes on within the interconnect within a network on chip, the latency is much lower than the interconnect that goes to connect server systems together in a data center. And what you see here is that the way I broke it up was we have the on chip, which is the SoC level, so it's the network on chip. We have die to die. As we get outside the package, we have chip to chip. As we get onto the board, we have the board interconnect. And at the server and the system level, we have the system interconnect. These are the cables connecting different devices together, in the data center or in your car.
And one of the things that you have to realize is that everything on that chip has to move faster than it does up at the system level, right? So your network on chip has to move at the speed of this doesn't go off chip. Everything on chip is faster.
Exactly. So here you're dealing in nanoseconds, even picoseconds. When we go to here, you're dealing with milliseconds. So that's a big difference. Another thing that happens when you talk to somebody and you say network on chip interconnect, sometimes they say, oh, it's network, it's networking. It's like TCP/IP. It's like taking what we do on Ethernet or InfiniBand or something like that and just shrinking it into a chip. And that's totally not true. Each of these different interconnects at the different levels are optimized for the types of communications that they need to do at that physical level.
And this goes down even further, right? Because now you're dealing with interconnects at level 1 and level 2 of the metal that goes into the die itself, and then it comes up into the logical area, which is where the knock is.
That's exactly true. My first job out of business school was as a supervisor of the thin films part of a research and development fab. And when you said interconnect, what we were talking about were those metal layers where we were doing chemical vapor deposition and PVD to create those things. We're talking about vias that we're filling with tungsten. We're talking about copper. For the different layers. So when you're talking interconnect, that's what you were talking about.
And when you think about latency now, you're dealing with a whole series of pieces that lead up to your ultimate system latency, right? So each one of those has to be measured and they're all potentially additive.
That's correct. And what's interesting is that each of these different layers of communication throughout the whole system for it to all work, has to make assumptions about what they're going to get for inputs and outputs from the lower layers. And if you're wrong on those assumptions, then that affects the overall system level performance capabilities, which are bandwidth and processing capabilities, as well as, in many cases, latency is a huge issue, let alone power.
If you're building a network on chip, what level are you actually at within the system? Are you at the architectural level? Are you at the implementation level?
Well, what's interesting that people don't understand all the time is the network on chip is the physical and logical instantiation of whatever that SoC architecture is. So when the architects get together and say, hey, we're going to have this IP and that IP and that IP and that IP, if you look at a bunch of different chips in an industry, they'll all have similar ARM clusters, similar memory controllers, similar ingredients, if you will. But the recipe of how these are put together is often very, very different. And the instantiation of that recipe is the NoC interconnect. Those NoC interconnects are all totally different from each other. And for any chip, that NoC IP is the one thing that's always different no matter what.
So, Kurt, how does data actually move through all these systems?
So it's a mix of digital packets as well as analog signals going through the system. If you're dealing up here at the system level, let's say we're dealing with Ethernet and InfiniBand, those are standards, there's packets within those, and then at the lower layers, at the physical layers, there's a signaling specification. You have similar specifications at the board level. We have for chip-to-chip type standards like CXL, there's some physical, which is PCIe, as well as logical, as far as the packet descriptions of how that communication goes there. Die-to-die, C6 is an example of that. And then within the network on chip interconnect, we also have some standards. So there's packets going through, there's transactions and signaling coming through here defined by the ARM AMBA specifications or OCP. And then for the different NOC technologies, there's a standardized packet structure within that.
Kurt Shuler, thanks for a great introduction on this.
Hey, thanks, Ed.